Historically, I mean, database management meant spending your entire weekend in a freezing data center, right?
Wearing the puffy jacket.
Exactly. The puffy jacket, your fingers are completely numb, and you're physically unracking servers, like literally swapping out failing hard drives.
It was a nightmare.
Total nightmare. But today, well, it's just a few clicks in the cloud. But here's the terrifying part, I think. Those abstractions, they hide the actual physics of data storage and network latency.
They absolutely do.
And if you make the wrong architectural choice today, you aren't just losing a single hard drive. You could permanently corrupt your entire company's data.
Yeah, the shift from that tactile, hardware-based infrastructure to virtualized cloud services, it didn't eliminate the complexity at all. It honestly just moved it.
Right.
So now, instead of worrying about CD5 cables and, cooling systems, database engineers have to worry about synchronous versus asynchronous replication.
Which is incredibly complex.
It is. You're dealing with hypervisor-level storage constraints and the absolute chaos of distributed systems split brain.
Which sounds like a sci-fi horror movie, and we will definitely get into that. But that is exactly what we are dissecting in this deep dive.
Yeah, it's a huge topic.
So if you are tuning in, you are likely navigating these exact architectural choices. Or maybe, perhaps you're actively preparing for the Google Cloud Professional Database Engineer certification, the PCDBE.
Right, the PCDBE.
And we are pulling our insights today from a really highly targeted source. It's a slide deck designed specifically to prepare technology professionals for that exact certification journey.
Which is great because it means we're looking at this through a very specific, unforgiving lens.
Yeah. No fluff.
Exactly. We aren't just talking about theory here. We are looking at best practices, the hard architectural trade-offs, and, well, the specific disaster scenarios that Google expects an expert to know how to resolve under pressure.
Right, because the exam does not pull punches.
Yeah.
So the mission for our conversation today is to map out the critical boundaries between managing your own database infrastructure versus handing the keys over to a managed service like Cloud SQL.
Which is the big debate right now.
It is. We are going to break down the exact mechanisms of keeping a database alive when hardware inevitably fails. So let's just start by looking at the absolute baseline.
The do-it-yourself dilemma.
Yes, the do-it-yourself dilemma, as the source calls it. Running self-managed databases directly on Compute Engine.
So the source material lays out the traditional on-premises stack first, just to set a baseline for operational toil. Like, if you are running a database in your own data center, your team owns everything.
Literally everything.
Yeah, you own the application logic, the scaling parameters, the high availability architecture, plus routine database maintenance, security patching, the host operating system.
And the physical concrete floor the server sits on.
Right, you own the concrete.
It's a massive surface area to defend. Now, moving that workload to Google Compute Engine, or GCE, which is Google's infrastructure as a service layer, that gets you out of the physical data center business, right?
Yeah, absolutely.
You no longer care if a literal backhoe cuts a power line or if a physical memory stick goes bad in Rack 4. Google handles the physical layer and the hardware virtualization. But the list of things you still have to do is pretty daunting.
It's basically everything else. You are essentially just renting a very reliable virtual motherboard and CPU.
Right.
The entire software and operational stack above that hypervisor is still your problem.
Yeah.
So you are still patching the Linux or Windows OS yourself.
Patching.
Yeah. You are still configuring the database engine parameters. You're still solely responsible for backup, scaling, and engineering failovers.
And the deck goes into the weeds on how you actually bootstrap these self-managed databases on GCE. It's not a single path. You have options, but they all require, significant engineering overhead.
They really do.
For instance, they highlight startup scripts. You can inject Linux Bash scripts or Windows PowerShell scripts directly into the virtual machine's metadata. So every time that VM boots, it executes the script.
Let's visualize what that script is actually doing for our listeners, because it isn't just a simple line saying start database.
Right. It's way more complex.
Exactly. A robust Bash startup script might have to pull the latest security keys first. Then it has to reach out to an external repository via an apt-get or yum command, download specific versions of PostgreSQL, install them.
And configure them, I assume?
Oh, heavily. It has to modify the PostgreSQL.conf file to set your shared buffers and memory limits based on that specific machine type. Then configure the pghba.conf for network access, and then finally start the system daemon.
Wow. And the source actually shows a command line example where a developer is creating a VM, attaching a boot disk, and passing this massive, dense string of bash commands right into the Cloud Compute instance's create command.
It's a huge block of text.
It is, and if you miss a single semicolon in that script, the VM boots up, but your database silently fails to start. It just relies entirely on your own rigorous testing pipeline.
Which can be incredibly brittle. So to mitigate that brittleness, the material outlines slightly more automated paths you can take.
Like what?
Well, you can leverage Google Cloud Marketplace deployments. These are prepackaged, vetted deployment templates.
Oh, okay. So someone else wrote the script.
Basically, yeah. You can go to the marketplace, select MongoDB, Couchbase, Redis, PostgreSQL, MySQL, or CockroachDB. And Google's deployment manager will handle that initial VM provisioning and the software installation for you.
That seems way safer. And they also highlight public, pre-built OS images, which I guess is a big deal for Microsoft SQL Server workloads.
It's a massive deal.
Yeah.
Google maintains images for SQL Server 2014 all the way through 2019, covering the Express, Web, Standard, and Enterprise editions.
And there's a really important financial detail baked in here for the exam, right?
Yes. The license fee for SQL Server is natively included in the hourly compute rate you pay for that specific VM image.
So you don't have to manage a separate license key if you don't want to.
Right. Though they do carefully note that if an enterprise already has a massive agreement with Microsoft,
Yeah.
they don't have to double pay.
No, that makes sense.
Yeah. Bring your own license, or BYOL, is fully supported through the Microsoft License Mobility Program that allows you to run your own licensed SQL Server on a base Windows Server image.
Okay, so you use a marketplace template or a pre-built OS image, you click a few buttons, the VM spins up, and the SQL Server is running. I mean, that doesn't sound like a nightmare. Why is the source so adamant that this DIY approach is a dilemma?
Because honestly, installation is the easiest part of a database engineer's job.
Fair point.
What happens on day 2? You now have an empty database. You still have to manually provision the storage to ensure it hits your IOPS targets. You have to manually apply security patches next month.
Yeah, the day 2 operations.
Exactly. If the VM dies, you have to write the automation that detects the failure and brings up a new one. The operational toil hasn't disappeared at all. It is just shifted from racking hardware to writing bash scripts and managing state.
And the source makes this a very explicit exam tip. Like, self-managed databases on Compute Engine are not a preferred option from the certification perspective, unless you have a highly specific, valid architectural constraint that forces you to use it.
Right. The underlying philosophy of cloud architecture is to offload non-differentiating heavy lifting. Managing base-level database VMs, it rarely gives a business a competitive advantage.
Right, doesn't make your product any better. So to really understand that heavy lifting, we need to dive into where the data actually lives in a DIY setup. Because in Compute Engine, you are dealing with persistent disks, or PDs.
Yeah, persistent disks. They are network-attached block storage volumes, and the key word there is persistent.
Meaning they outlive the VM?
Exactly. They have a life cycle that is completely independent of the virtual machine they are attached to. If you delete your database VM, the disk and all your customer data on it remains perfectly safe and available to be attached to a different machine.
And the deck breaks these disks down into several tiers. If you're architecting a system, you have to match the disk physics to your workload.
You do.
So at the base level, you have standard PDs. These are backed by traditional hard disk drives, like spinning magnetic platters.
Which, in a modern context, standard HDDs sound antiquated. But they have a very specific use case.
Like cold storage?
Yeah. They are highly sensitive to cost, and they excel at sequential read and write operations. So if you were dumping a massive, continuous stream of cold backup logs, a standard PD is incredibly cost-effective.
But not for a live database.
No, if you try to run a transactional relational database on them, the random read and write latency will just completely crush your application's performance.
Right. So for those transactional databases, you move up to the solid-state drive tiers. You have balanced PDs, which give you the best price per gigabyte for general-purpose workloads.
Right.
And then you have performance, or SSD PDs, engineered for the best price per IOPS, meaning input-output operations per second. I think this is where most standard database workloads end up.
Yeah, that's the sweet spot for most. But if you need to push the envelope further, the source mentions extreme PDs.
Extreme PDs sounds intense.
They are. They're designed for uncompromising performance and massive scale. Think of a massive in-memory database like SAP HANA.
Okay, yeah.
It operates incredibly fast in RAM, but it periodically needs to flush gigabytes of state to persistent storage instantly, just to ensure durability. Extreme PDs provide that massive throughput.
Oh, wow. And then there is the outlier here, which the material points out, local SSDs, and these are not network attached, right?
Right, they are physically slotted into the exact same physical server rack that is currently hosting your virtual machine.
Which means they offer the absolute lowest possible latency. You completely bypass the network hub.
You do, but there's a massive trade-off, and this is a frequent trap for architects. Local SSDs are ephemeral.
Meaning, poof, gone.
Exactly. If Google needs to take that physical rack down for maintenance, or if the underlying host crashes, that data is gone. It does not persist independently.
So you would never put a primary database on it?
Never. They're designed strictly for temporary caches, scratch space, or highly specific distributed databases like Cassandra that actually manage their own data replication across multiple nodes.
Okay, now here is where we hit a crucial exam tip regarding standard persistent disks. And frankly, this sounds like one of the most stressful parts of managing this infrastructure yourself.
Yeah, this rule trips a lot of people up.
The absolute rule is this. You can increase the size of a persistent disk online while the database is running without any downtime. But you cannot decrease the size of a persistent disk, ever.
Never. It is a hard, immutable limitation at the infrastructure layer. Once you provision that capacity, you are financially responsible for it until you delete the volume entirely.
Wait, hold on. Let me get this straight. You're telling me I can pay Google to instantly expand my disk from 1 terabyte to 10 terabytes if my company is doing like a massive Super Bowl marketing launch.
Big seamless expansion.
But if that launch completely flops and we only actually use 1.5 terabytes, I am permanently locked into paying for a 10 terabyte disk forever. I mean, that entirely contradicts the whole elasticity promise of the cloud. Why wouldn't Google just let me shrink it back down?
I know, it sounds crazy.
Yeah.
But to understand that limitation, we have to look past the cloud marketing and down into how block storage and file systems physically interact. This is an analogy.
I love analogies. Go for it.
Imagine buying a massive 10-acre plot of land to build a corporate campus. That land represents your 10 terabyte persistent disk.
Okay, I have my 10 acres.
Now you lay down a file system on it, say XT4 in Linux or NTFS in Windows. The file system acts like your campus architect. It starts building structures.
Okay.
It places a security building on acre 1, maybe a cafeteria on acre 4, an office building on acre 7, and a parking garage all the way out on acre 10. In a database context, your customer table might be on block 1, your index is on block 5000, and your transaction logs scattered across block 10 million.
Ah, so the data is heavily fragmented across the entire available capacity. It isn't just neatly stacked at the beginning of the disk.
Exactly. It's written wherever the file system finds an optimal space at that exact millisecond.
Okay, I'm following.
Now, the hypervisor, which is Google's underlying infrastructure that manages the persistent disk, it is completely blind to your file system's architecture. It just sees 10 acres of ones and zeros.
Right, it doesn't know what the ones and zeros actually are.
Precisely. So if you ask Google to shrink the disk from 10 terabytes down to 2 terabytes, the hypervisor doesn't know how to carefully move your buildings. It would essentially just take a massive saw and blindly chop off the last 8 acres.
Oh, wow. And if my critical database index files were sitting on acre 7, they are instantly severed. The database is corrupted and unrecoverable in a fraction of a second.
It is a catastrophic event. To safely shrink a disk, you would need the file system inside the operating system to painstakingly defragment itself first.
It's like the old Windows defrag tool.
Exactly like that. It would have to move every single block of data from acres 3 through 10 into the first 2 acres, update all its internal master file tables and inode pointers, and then signal to the hypervisor that it was finally safe to sever the remaining space.
Which sounds insanely complicated.
It is. That level of cross-layer orchestration is incredibly risky and specific to dozens of different file systems. So, cloud providers draw a hard line. They will easily append more empty land to the end of your property to grow it, but they will never, ever risk corrupting your data by arbitrarily chopping land off.
Wow, okay. So if I make that architectural mistake and I over-provision by 8 terabytes, what is my actual operational recourse to stop paying for that empty space?
Your only option is entirely manual.
Oh, no.
Yeah, you have to provision a brand new, smaller 2 terabyte disk. You attach it to the VM, you format it, you manually copy all your database files from the 10 terabyte disk over to the new one.
That sounds like it takes forever.
It does. Then you reconfigure your database engine to point to the new mount path, restart the database, and then finally delete the massive 10 terabyte mistake, all of which implies a significant scheduled downtime window for your application.
That deep dive right there into the physics of storage,
Yeah,
That perfectly highlights what the exam material means by operational toil.
absolutely.
It's not just the labor of typing commands. It's the architectural constraints and risks you have to meticulously plan for. So, if managing block storage fragmentation and capacity planning manually is this risky, how do you escape it?
Well, before you can choose a managed service to handle it for you, you have to have a very uncomfortable conversation with your business stakeholders about failure.
Right. Section 2. The business of continuity. The source material pivots here to the core rules of business continuity. Before you architect anything, you have to define the acceptable parameters of a disaster.
Which relies on two absolute foundational metrics that govern every single decision a database engineer makes: RPO and RTO.
Let's define them for our listeners. RPO stands for Recovery Point Objective, and the material defines this as the maximum acceptable amount of data loss during an outage.
Right, data loss.
And RTO is Recovery Time Objective, which is the maximum acceptable amount of time it takes for normal service to resume after an outage.
So they measure the two critical dimensions of any failure: how much history you lose and how long you were paralyzed.
So, to use an analogy, RPO is like realizing you forgot to save your Word document. It's the amount of writing you have to redo.
That's a great way to put it.
And RTO is how long it takes your computer to reboot so you can actually start typing again.
Exactly. And for those of you running these systems, RPO isn't just an abstract concept. It fundamentally dictates your storage architecture.
How so?
Well, if you are running a social media application's caching layer, your RPO might be 5 minutes. If the cache dies, you lose the last 5 minutes of likes and view counts. The business might accept that.
Right. Nobody is going to sue you over a lost like.
But if you are managing the central database for a financial clearinghouse, your RPO is 0. You absolutely cannot lose a single committed transaction, which means you cannot rely on periodic backups. You need synchronous replication.
And RTO dictates your compute and routing architecture, right?
Exactly. If your RTO is 24 hours, you can afford to restore a database from a cold backup tape. If your RTO is 5 seconds, you need hot standby servers constantly running and automated load balancers ready to reroute traffic instantly.
Okay, now, the slide deck makes a very sharp distinction between two concepts that businesses often blur together: high availability, or HA, versus disaster recovery, or DR. The deck insists that you must define separate RTO and RPO metrics for both scenarios.
This is a critical distinction for the exam.
Uh-huh.
High availability is about surviving a localized physical hardware failure. In Google Cloud terminology, HA handles zonal failures.
And a zone is essentially a single physical data center, right? Or a distinct section within a larger one.
Yeah, exactly. Like if a server rack's top-of-rack switch bursts into flames, or a power distribution unit for one specific building trips and dies.
The goal of HA is automatic discovery and resolution of those specific failures.
Right. The system must notice the failure and heal itself without a human engineer ever waking up to an alert. And because zones are located geographically close to each other within the same region, the network round-trip time between them is incredibly fast.
Like under 1 millisecond?
Typically, yes. And that speed allows HA to rely on synchronous replication.
Meaning, when a user's application sends a commit command to save data, the primary database writes the data to its own disk, then immediately sends that data over the network to the backup database in the second zone.
And it waits.
Right. It waits for the backup to confirm it also successfully wrote to its disk, and only then does the primary database tell the user success.
And that synchronous replication guarantees 0 data loss, an RPO of strictly 0, because the transaction isn't considered complete until it exists in 2 separate physical facilities.
Which is amazing. But disaster recovery, on the other hand, handles regional failures.
Yes. A region in Google Cloud is a massive geographic area, like US Central 1 in Iowa or Europe West 3 in Frankfurt, which contains multiple distinct zones.
So if a massive natural disaster, like a hurricane or a regional power grid collapse, takes out the entire geographic area, all of your zones go offline simultaneously, that is a disaster.
Yes, that is a true DR scenario.
Mm-hmm.
And the source notes that DR procedures are typically manual or semi-automatic. It requires a human being to look at the dashboards, confirm that the primary region is truly gone, and not just experiencing a temporary network blip,
Right.
and then make the executive decision to fail over to a backup region across the country or across the globe.
And the key physical constraint here is literally the speed of light, isn't it?
It is. The network round trip between geographic regions is much slower, ranging from tens to hundreds of milliseconds.
Yeah.
You cannot use synchronous replication over those distances without introducing massive latency or into every single database transaction.
Your app would feel incredibly slow.
Unusably slow. Therefore, DR almost always relies on backups or asynchronous replication.
So with asynchronous replication, the primary database writes the data, immediately tells the user success, and then in the background streams those transaction logs over the long-distance network to the backup region.
Which means if the primary region suddenly explodes while data is in transit across the country, those specific transactions are permanently lost.
Just as
Gone.
Hmm.
Therefore, DR inherently implies an RPO greater than 0. The business has to accept some data loss to survive a cratered region.
Let's bring this back to the DIY dilemma for a second. The material delves into how you would actually construct a self-managed high-availability setup on Compute Engine to protect against those zonal failures with zero data loss. And they highlight a highly specific GCP storage feature for this: regional persistent disks.
Oh, regional persistent disks are a fascinating piece of infrastructure engineering. We talked about standard zonal persistent disks earlier. A regional PD takes that block storage layer and performs synchronous replication across two separate zones within the same region, entirely at the hypervisor level.
So the replication logic is completely invisible to the SQL Server or PostgreSQL database engine running inside the virtual machine.
Completely invisible. The database engine mounts the drive and simply thinks it's writing to an incredibly reliable local hard drive. Underneath, Google's infrastructure is intercepting every block write and ensuring it is committed to both Zone A and Zone B simultaneously before acknowledging it.
And the slide deck emphasizes this doesn't violate latency budgets because the zones are connected by Google's dedicated, privately owned fiber network.
Exactly.
So the deck outlines the exact operational sequence when a zone dies in this setup. Let's say your primary database VM is running in Zone A, attached to this regional PD. Zone A suffers a catastrophic power failure. The VM instantly dies.
The storage, however, is perfectly safe because every block was synchronously replicated to Zone B. The recovery procedure involves provisioning a brand new virtual machine in Zone B and issuing a specific API call, a force-attach command to grab that regional PD and mount it to the new VM.
The deck explicitly states this force-attach process takes time, usually under a minute.
Yeah, it takes time because the underlying storage infrastructure has to run through a safety protocol. It has to securely sever the distributed locks that the dead VM in Zone A held on that disk. It has to guarantee Zone A is truly fenced off before it grants read and write access to the new VM in Zone B to absolutely prevent any chance of block-level corruption.
Okay, now the source also explores how a team might handle the broader disaster recovery requirement in a hybrid cloud scenario. Imagine your primary database is sitting in your own physical data center on premises, and you want to use Google Cloud as your DR site.
Right, hybrid DR.
They outline 3 architectural approaches: cold, warm, and hot.
The cold approach is the most cost-effective, but yields the slowest recovery. This involves taking your daily or hourly database backup files from your data center and moving them into Google Cloud Storage, which is basically an infinitely scalable repository in the cloud.
The deck suggests scripting a tool like a Justal rsync triggered by a local cron job to sync the backup files over the internet or a VPN.
But the deck bluntly warns the reader, offloading backups to GCS does not really mean you have a DR procedure. It just means your historical files are safe off-site.
Right, your RTO, the downtime would be massive. If your data center floods, you have to log into GCP, manually provision new Compute Engine VMs, install the database software from scratch, download terabytes of backup files, and run the restoration process before you can even begin testing.
It could take days.
Yeah.
So to drastically improve that RTO, they outline an optimized cold approach. You still ship the backup files, but you also prepare a dormant recovery server in GCP.
Oh, like a pre-baked image.
Exactly. You build a custom OS image with your specific database engine and all necessary dependencies already installed and configured. If a disaster strikes, you spin up a VM from that image, copy the backups, and restore them. It saves hours of installation time.
And if the business demands a much tighter RPO, meaning minimal data loss, you have to move to the warm or hot approach. Here, you create a VM in GCP ahead of time, leave it running 24/7, and configure asynchronous database-level replication from your on-premises database directly to the cloud VM.
This approach dramatically lowers your RPO and RTO, but as the slide material warns, it shifts the burden to network engineering.
Yeah, it sounds like a networking headache.
It is. You require intense network preparation. establishing dedicated cloud interconnects or high-availability VPNs, configuring complex VPC subnets, custom firewall rules, and split-horizon DNS routing to ensure the replication traffic securely traverses the hybrid boundary without interruption.
Let me stop you right there, though, and go back to that DIY high availability setup using regional persistent disks within GCP.
Sure.
If I set up a regional PD that replicates my storage synchronously between two zones with zero data loss, and if my primary zone goes down, I just run a quick script to force attach the disk to a new VM in zone B in under a minute,
Okay.
haven't I effectively solved the high availability problem?
Well, sort of.
Why does the exam material still heavily frown upon this DIY approach? It sounds like I fixed it.
That is the exact logical trap many engineers fall into. The short answer is, you solve the storage replication problem, but you completely ignore the application state problem.
Walk me through that. What state is missing?
Think about what a database engine actually is. PostgreSQL or SQL Server isn't just a simple process writing to a disk. It is a highly complex application managing gigabytes of data in active RAM. Shared buffers, query caches, execution plans.
Okay, yeah.
When the power is abruptly cut to zone A, that engine crashes instantly. It doesn't gracefully flush its memory to disk. It doesn't neatly close its transaction logs.
Right, it's a violent crash, like pulling the plug on a desktop.
Exactly. So when you forcefully attach that disk to the new VM in zone B and start the database daemon, the engine doesn't magically know it's supposed to be taking over seamlessly.
Oh, I see.
It boots up, looks at the disk, and sees that the write-ahead logs are dirty. It realizes a crash occurred. Before it can accept a single client connection, it has to perform an emergency crash recovery process, scanning the logs, rolling forward committed transactions that were in memory, and rolling back uncommitted ones.
And how long does that take?
Depending on the transaction volume, that crash recovery could take minutes or even hours.
So even though the storage disk is instantly attached, the database itself is paralyzed, trying to fix its own internal logic.
Yes. And let's look beyond the database engine to the routing infrastructure you have to build to make this work automatically. You can't just have a script on your laptop. You need to configure a managed instance group, a MEG, in GCP to constantly monitor the health of the primary VM.
Right.
If it fails, the MEG has to automatically provision the new VM in zone B, execute the force attach API call, start the database service, wait for the crash recovery to finish, and then critically, you need an internal load balancer sitting in front of all of this.
Because the IP address of the newly spawned VM in Zone B is going to be completely different than the dead one in Zone A, the web servers trying to reach the database have no idea the IP changed.
Precisely. The application tier is pointed at the static IP of the load balancer. The load balancer has to actively health check the instances. It has to detect that Zone A is dead, detect that Zone B is finally healthy and has finished crash recovery, and then dynamically reroute all TCP traffic to the new instance.
That is a lot of moving parts.
It's immense. Building, testing, and maintaining the flawless execution of that entire choreography, the health checks, the instance groups, the storage API calls, the crash recovery, the routing table updates, is immensely difficult. The complexity of maintaining data consistency and network routing during a violent, unpredictable failover event at 3 a.m. is staggering.
Because rebuilding that RAM state and routing layer during a 3 a.m. pager alert is an absolute nightmare, most enterprises simply give up on DIY.
Yeah, they really do.
They look at that required engineering effort and realize it provides zero competitive advantage to their actual business. And that brings us directly to Section 3, the managed portfolio and the dominance of Cloud SQL, where Google handles the RPO and RTO heavy lifting for you.
The Google Cloud Database Portfolio is extensive. They recognize that a single database architecture cannot solve every problem, so they map specific managed services to specific operational and analytical needs, categorizing them by relational or NoSQL data structures.
Let's do a quick flyover of the portfolio as outlined in the deck so our listeners know what tools are in the shed.
Sure.
For strictly in-memory workloads requiring microsecond latency caching, they have Cloud Memory Store, which is a fully managed Redis or Memcached service.
Yep. And for NoSQL document storage, think flexible schemas for user profiles, product catalogs, or real-time game state. They provide Cloud Firestore.
And for wide column NoSQL.
For wide column NoSQL, designed to handle massive, sustained write throughput and endless horizontal scale, think IoT telemetry data streaming from millions of sensors or financial time series data, they offer Cloud Big Table.
Moving to relational databases, which require rigid schemas, ACD compliance, and strict referential integrity, they have two main offerings. First is Cloud Spanner, which is an incredibly advanced, globally scalable relational database. And second is Cloud SQL, which is the primary focus of this specific deep dive.
Right. And finally, for the data warehouse side, for massive petabyte-scale analytics and BI dashboards, there is BigQuery.
But this deep dive is hyper-focused on Cloud SQL. It is a fully managed relational database service specifically supporting three engines: MySQL, PostgreSQL, and Microsoft SQL Server.
And the deck highlights just how dominant Cloud SQL is within the ecosystem. It is the most common managed database service in all of Google Cloud Platform.
Wow, really?
Yes, it is the most heavily tested managed database on the PCDBE exam. And crucially, it is utilized by over 90% of Google Cloud's top 100 enterprise customers.
That's a huge adoption rate.
It is the absolute workhorse of the cloud. The source includes a very telling quote from Tim Kelton, a cloud architect at Descartes Labs. He states, "Cloud SQL gives us more time to work on products that provide value to our customers."
That perfectly encapsulates the escape from the DIY dilemma. Instead of building custom load balancers and writing bash scripts to execute force-attached storage commands, Descartes Labs is spending their engineering hours building their actual geospatial analytics product.
Exactly. Cloud SQL backs that up with a 99.95% availability service level agreement. It features flexible maintenance controls, meaning routine version updates cause less than 30 seconds of downtime. It provides automated cross-region replicas and a critical feature called point-in-time recovery, or PITR.
Let's talk about point-in-time recovery because that sounds like magic.
It is an incredible safety net. Under the hood, Cloud SQL is continuously archiving your write-ahead logs to secure storage in the background. If a rogue developer accidentally executes a drop table command at 2:17 p.m. on a Tuesday, you don't have to restore yesterday's nightly backup and lose 14 hours of customer transactions.
Oh, thank goodness.
Yeah, you can literally instruct Cloud SQL to provision a new instance and replay the transaction logs exactly up to the state the database was in at 2:13 p.m., right before the catastrophic mistake was made.
That is amazing. Now, handing the keys over to a managed service implies a fundamental change in the relationship with your infrastructure. The expert deck illustrates this paradigm shift using the shared responsibility model.
This is a foundational concept for any cloud architect. When you adopt a managed service like Cloud SQL, you enter a partnership with Google. Google explicitly assumes responsibility for securing and operating the underlying infrastructure.
Meaning they handle the hardware?
Yes, the physical hardware, the data center network security, the host operating system patching, the database binary installations, and the automated failover orchestration logic.
So they patch the underlying Linux host without me ever knowing. That's great. But what remains on the customer's plate?
The customer remains entirely responsible for what lives inside the database and how it is accessed. You are responsible for securing your specific data, managing user access policies and IAM roles, writing efficient SQL queries so you don't overload the CPU.
So if I write a terrible query that crashes the DB, that's still on me.
Absolutely. And critically, you are responsible for actually choosing to architect for resilience. Google provides the high availability architecture, but you have to check the box, configure the network, and pay for the secondary instance to enable it.
Let's dig into why a company might specifically choose Cloud SQL for a Postgres workload, as highlighted in the deck. They point out that it uses standard open-source Postgres APIs.
Right, there is no proprietary lock-in. A standard Psychopata2 Python driver works the same way it does on your laptop. It integrates seamlessly with modern deployment platforms like Google Kubernetes Engine via the Cloud SQL Auth proxy and serverless platforms like Cloud Run.
They also heavily emphasize the default security posture. The data is encrypted by default while at rest on the persistent disks and while in transit over Google Global privately owned fiber backbone.
Yet your application traffic never traverses the public internet between regions. Furthermore, it integrates natively with analytical tools. You can use BigQuery's federated query feature to analyze your live Cloud SQL Postgres data directly from the data warehouse without having to build complex ETL data pipelines.
Okay, but wait. Earlier, we established an exam tip that said managed services are usually the preferred approach unless you have specific constraints.
Right.
We just spent 10 minutes outlining why Cloud SQL is basically magic. What kind of architectural constraint would actually force a team to abandon all of this managed goodness and go back into the freezing data center of the DIY nightmare?
It's an important reality check. Managed services enforce rigid boundaries. You give up ultimate low-level control to gain operational peace of mind. The deck lists several very specific considerations or hard limitations where Cloud SQL hits a wall.
What's the first one?
The first is if your application architecture absolutely requires super admin access to the database engine itself.
Like the SY-Sabin role in SQL Server or the Postgres superuser?
Exactly. In Cloud SQL, Google retains the ultimate super user privileges because they explicitly need them to perform automated maintenance, coordinate backups, and manage replication.
So I don't get root access.
You don't. You are provided with a highly privileged user role, like Cloud SQL superuser, but not the absolute top-tier root admin. If you have a legacy enterprise application that stubbornly hard codes a requirement for SQL SQL rights to execute custom system stored procedures, it will simply fail to run on Cloud SQL.
That makes sense. What's another constraint?
Zero downtime requirements for maintenance. As we mentioned, Cloud SQL provides flexible maintenance controls, but applying a kernel patch to the host or a minor version update to the database engine still requires a brief restart of the service, typically less than 30 seconds.
Which doesn't sound like much.
Not to most of us, no. But if you are operating a high-frequency algorithmic trading platform where 30 seconds of drop connections cost the firm millions of dollars, you cannot tolerate Cloud SQL's maintenance windows. You have to build a custom, highly complex rolling upgrade cluster yourself on GCE.
Oh, wow. And I imagine specific niche plugins are an issue too, right? Like if you rely on a third-party C extension module for Postgres that Google hasn't officially vetted and installed on their managed images?
Precisely. You can't just SSH into the server and run a make install command because you literally do not have access to the underlying OS shell.
Right.
If your application architecture runs into those tight constraints, you have no choice but to absorb the operational toil and manage it yourself on Compute Engine. But for the vast majority of standard web, mobile, and enterprise workloads, the trade-off of losing shell access is more than worth the operational stability.
When you accept those boundaries and opt into the managed service, what exactly are you buying when things break? Let's move into Section 4 and explore Cloud SQL high availability, or surviving the zone.
We talked exhaustively about how difficult DIY high availability is. Now let's examine how the managed service orchestrates it. The Cloud SQL HA architecture is incredibly elegant.
Okay, break it down for me.
It consists of a primary database instance and a standby secondary instance, and they are intentionally provisioned in different zones within your chosen region.
So your primary instance is humming along in Zone A, and your standby is in Zone B.
Right. And similar to the regional persistent disk concept we discussed earlier, Cloud SQL HA relies on synchronous replication to each zone's persistent disk. Every single write transaction and insert, update, or delete is committed to the persistent disk in Zone A and synchronously confirmed on the persistent disk in Zone B before the database engine acknowledges the success to your application.
Guaranteeing zero RPO, absolutely no data is lost if Zone A vanishes into a single.
Zero data loss, yeah.
The deck outlines the precise trigger for this automated failover mechanism. There is a continuous health heartbeat monitoring the primary instance. If that heartbeat fails to respond for approximately 60 seconds, the control plane initiates an automatic failover.
And the orchestration that happens next is entirely abstracted away from the customer. Google's control plane detects the failure. It forcefully fences off the primary to ensure it can't cause corruption, attaches the synchronized persistent disk to the standby virtual machine in Zone B, starts the database engine, and performs any necessary crash recovery in the secondary.
And the most magical part, the part that solves the massive headache we discussed in the DIY section, is that the standby instance takes over using the exact same static IP address for the client application.
Yes. It's seamless for the network layer. Your web servers might experience a transient connection timeout for a minute or two, but they simply retry connecting to the same IP, the connection succeeds in Zone B, and the application keeps working. No load balancer reconfiguration or DNS updates are required by the customer.
That is brilliant.
This architecture is technically referred to in the documentation as a failover replica, and there are some crucial operational exam tips associated with configuring it.
Yes.
First, changing a standard single-zone Cloud SQL instance into a high-availability instance can be executed with a single click in the console.
Or via the command line, which the exam loves to test. The deck provides the specific syntax: gcloud sql instances patch instance name -- availability -- type regional.
Good memory. However, while it is just one click or one simple command, making that architectural change requires the primary database instance to restart to take effect.
Mhm.
It is not a hot, seamless change.
That is a critical operational detail for planning. You can't just decide to flip HA on in the middle of a busy Black Friday rush without briefly interrupting live traffic.
Exactly. You take the site down.
Now let's talk about the financial reality of this setup, because you are fundamentally provisioning two distinct virtual machines. One in Zone A, one in Zone B LNJ configured instance, is charged at double the price of a standard standalone instance.
You are paying for the physical compute CPU and memory of that standby server 24 hours a day, 7 days a week, just in case disaster strikes.
Which leads to another crucial detail highlighted in the deck, and this is where engineers often get really frustrated.
Oh, and I know what you're going to say.
The standby instance cannot be used for read-only access. It just sits there, consuming your budget, doing absolutely nothing except receiving synchronous block-level storage updates. You cannot run analytical reports against it. You cannot offload heavy select queries to it.
It is an entirely passive dormant node. And furthermore, routine maintenance for HA-enabled instances still requires downtime. The automatic failover mechanism is expressly not used to keep the database online during routine scheduled version updates.
Wait, I have an analogy for this. This HA setup sounds exactly like a Hollywood movie production hiring an incredibly expensive stunt double to stand by on set.
Okay, I like where this is going.
The lead actor is the primary instance. The stunt double is the standby. But you're telling me I have to pay double the salary for the stunt double? They aren't allowed to do any background acting to earn their meaning no read-only queries. ND, if the lead actor needs to take a scheduled 30-second break to drink some water for routine maintenance, the stunt double just stays hidden in their trailer and the entire million-dollar movie production completely halts.
Yeah, that's pretty much it.
Why on earth wouldn't Google use the standby failover to keep the database actively running during maintenance? It just seems like a waste.
The stunt double analogy perfectly captures the financial frustration. It really does. But it misses the actual physics of the network.
How so?
The reason that standby stays in the trailer during maintenance isn't a limitation of the software. It is a deliberate protective design to avoid the ultimate distributed systems nightmare: split brain.
Let's dissect split brain for the listeners, because we mentioned it earlier and it sounds like the plot of a sci-fi horror movie.
It is the database equivalent of a horror movie. Split brain happens when the network link connecting Zone A and Zone B breaks, but the actual servers in both zones are still perfectly healthy and running.
So they just can't talk to each other.
Right. The primary database in Zone A looks at its network interface and thinks, I can't reach the standby heartbeat. It must be dead. I'll keep accepting customer data. Simultaneously, the standby in Zone B thinks, I can't reach the primary's heartbeat. It must be dead. The rules say I must take over as the new primary and start accepting data.
Oh no! So suddenly, you have two independent primary databases completely isolated from each other, both accepting conflicting write transactions.
Yes.
Imagine a retail site during a massive sale. Customer A buys the absolute last television in stock, and the transaction is routed to Zone A. A second later, customer B buys that exact same television, and the transaction is routed to Zone B. Both databases confirm the sale.
Exactly. And the horror happens when the network link is finally restored an hour later. The databases see each other and realize their transaction logs have completely diverged. Reconciling that diverging data mathematically is nearly impossible without massive manual data loss. You literally sold a TV that doesn't exist.
That's a disaster.
Therefore, failovers are designed to be violent, decisive events reserved strictly for actual disasters. When a failover triggers, the Google control plane forcefully isolates the old primary, revokes its access to the persistent storage locks, and mathematically guarantees it cannot accept traffic before promoting the standby. It's a highly disruptive emergency procedure.
So applying that terrifying reality to routine maintenance.
Routine maintenance is a controlled, highly predictable event. If Google triggered an emergency failover just to apply a minor OS security patch, they're introducing massive, unnecessary architectural complexity and risking a split-brain scenario just to save 30 seconds of downtime.
That makes total sense.
Furthermore, after the failover completes, your database is now permanently running in Zone B. To get your architecture back to its normal state, you'd have to execute a failback to Zone A, which is another violent disruptive event. It is infinitely safer and cleaner to just gracefully pause the primary instance, apply the patch, and restart it in under 30 seconds, rather than unnecessarily detonating a complex failover sequence.
That reframes it entirely. You don't pull the emergency eject seat handle on a fighter jet just to adjust your seat cushion. You endure the 30-second pause to guarantee absolute mathematical data integrity.
Precisely. And as for why the standby node can't accept your read queries to save money, because the synchronous replication is happening at the low-level block storage layer, not at the database engine logical layer.
So it's not like a standard replica.
No, the standby database engine isn't actively processing SQL commands or building query plans in memory. It's just passively watching the raw disk blocks change underneath it. It physically isn't in a state to parse and answer a select query safely.
That perfectly explains the boundaries of high availability. It protects a building, it guarantees zero data loss within a localized area. But what if the entire geographic region goes offline? What if you need to scale out your read queries to thousands of users globally?
That brings us to Section 5, Disaster Recovery and Read Replicas, where we have to abandon synchronous block storage and enter the complex world of asynchronous replication.
Surviving the region requires a different architecture. When we talk about true multi-region disaster recovery, offloading heavy analytics, or migrating platforms, Cloud SQL utilizes read replicas.
Right.
A read replica is exactly what it sounds like. It is a separate, fully running database instance that continuously copies data from your primary instance, but it enforces a strict rule. It only allows read-only queries. It outright rejects any application attempting to write or modify data.
And the slide deck points out you can have a massive scale-out architecture attaching up to 10 read replicas to a single read-write primary instance.
And
Yeah. And here is a highly specific fun fact the exam loves to test. If you are using the MySQL engine specifically, you can actually execute DDL commands to create additional custom indexes directly on the read replica itself without those indexes existing on the primary.
really, why would you do that?
It is brilliant for analytics. If your data science team wants to run massive, heavy analytical reporting that requires scanning millions of rows using specific composite indexes, you can build those indexes on the replica. The queries run lightning fast for the analysts, but you don't bloat the primary transactional database with unnecessary indexes that would slow down your core application's insert speed.
That is a great trick. Now, the source outlines several architectural options for replication. You can configure standard GCP to GCP replication, either within the same region-to-scale reads or across completely different geographic regions.
You can also configure an external read replica that continuously replicates data from a Cloud SQL primary up in GCP down to a legacy database still running in your on-premise data center.
And the reverse pipeline is also fully supported, right?
It is. You can replicate from an external on-premise server up into the cloud using the Database Migration Service, or DMS. This service pulls the transaction logs from your legacy data center and streams them into a Cloud SQL replica, which is exactly how modern enterprises perform zero downtime migrations into the cloud.
Let's focus our attention on disaster recovery using cross-region read replicas. This is how you protect your business against a massive multi-zone regional outage, like US Central 1 going completely dark.
Right. You provision a read replica in a completely different geographic region, say US East 4 in Virginia. The data is replicated asynchronously over the long-distance network.
And we must highlight a crucial operational warning from the deck regarding the sizing of these DR replicas. Engineers often try to save budget here, but the deck explicitly warns do not use small instance configurations for your cross-region replicas.
Very important warning. They specify avoiding instances with less than 2 virtual CPUs, less than 100 gigabytes of disk space, or using standard HDD persistent disks.
But why the strict minimums? If it's just sitting there passively waiting for a disaster that might never happen, why not make it as cheap as possible?
Because of the physics of replication lag. Asynchronous replication requires the replica database engine to actively process the continuous stream of transaction logs coming over the wire from the primary.
Okay, so it has to work to keep up.
Yes. If the primary is a massive 16-core machine processing thousands of complex transactions a second, and your replica is a tiny 1-core micro-instance, it literally will not have the CPU cycles to write the data fast enough to keep up. The replica will fall further and further behind real time.
Oh, I see. And if a disaster suddenly strikes the primary region when that underpowered replica is 6 hours behind on processing the logs, your RPO, your permanent data loss, is 6 hours.
The reality is your entire DR plan is completely useless if the replica isn't robust enough to keep pace with the primary's workload.
Okay, so let's play out the scenario. A regional outage occurs. The primary region is dead, the dashboards are red, the deck outlines the exact disaster recovery procedure you must follow. And here is the kicker for anyone used to the magic of HA. You must manually intervene to promote the read replica to become a standalone read-write primary database.
It absolutely does not happen automatically.
If you're listening to this and you've ever had to run a weekend DR test, you know the exact pit in your stomach we're talking about right now, that moment when you hover your mouse over the promote button. But why is it manual? If high availability within a zone is so elegantly automated by Google, why is disaster recovery so stressful? Why doesn't Google just click promote for me when the region goes dark?
We come right back to the terror of the split brain scenario we discussed, combined with the reality of asynchronous replication. Because the cross-region replication is asynchronous, there is always an inherent delay. It might only be 200 milliseconds of network transit time, but there is always a gap between what the primary committed and what the replica received. If the primary region goes dark, there are absolutely transactions that were confirmed to the user on the primary, but hadn't quite made it across the country to the replica yet.
So clicking promote on that replica means formally accepting that those in-transit transactions are gone forever.
Yes. Promoting an asynchronous replica forces an RPO event. It forces literal data loss. Google, as a cloud provider, fundamentally refuses to make an automated algorithmic decision to permanently lose your company's data.
Wow, so it's a liability thing too.
Partly, yeah. A human being, a lead database engineer or a CTO, has to look at the situation, determine that the primary region is truly destroyed and not just experiencing a 30-second network blip, and explicitly make the business decision to sever the replication tie, accept the data loss, and promote the replica.
Because if Google automated it and it was just a transient 10-second network routing blip,
The replica in Virginia would automatically promote itself and start accepting new customer orders. 10 seconds later, the primary in the central region comes back online, realizes it's healthy, and resumes accepting customer orders. You now have two primary databases moving in different directions, destroying your data integrity.
split brain again.
Exactly. By forcing a manual promotion, Google ensures a human assumes legal and operational responsibility for definitively severing the old architecture before authorizing the new one.
The slide deck goes into punishing detail on how you actually test this DR procedure, the full life cycle of failover and failback. And it proves your point about severing the old architecture. Let's walk through it because the exam will test these exact steps.
To properly execute a DR test, you start with your primary database, let's call it DB primary running in region A, and your cross-region replica DB replica running in region B. To initiate the failover test, you click Promote on DB replica.
It instantly drops its read-only restriction and becomes the new boss. It is now a standalone primary database actively running in region B.
Correct. You then update your application's DNS or connection strings to route traffic to region B. Now, your new primary is vulnerable because it's a single instance.
Right, it doesn't have a backup yet.
So to make it robust, you immediately enable high availability on it, turning it into a regional instance with a synchronous standby in region B. And to reestablish your global DR posture, you create a brand new cross-region read replica in a completely third region, say region C.
Okay, so the system is secure and highly available again. The test was a success. But what about the original DB primary sitting back in region A? Once region A comes back online, what happens to it?
This is the most counterintuitive part for many engineers and where they fail the scenario questions. To avoid any mathematical possibility of a split-brain situation or data corruption, you must definitively destroy the past.
Destroy the past.
The source material states explicitly, you must delete the original DB primary instance. Yes, it is outdated. It contains transaction data that diverged the exact millisecond you promoted the replica. It must never be allowed to receive application traffic again.
You literally click delete on the database instance that used to run your entire company?
You wipe it out entirely.
That requires absolute nerves of steel. And when the DR test is over and you want to fail back, when you want to return operations to the original data center in region A,
You have to orchestrate the entire dance in reverse during a scheduled weekend maintenance window.
Yep.
You create a new read replica inside region A, which pulls data from your current active primary in region B.
okay.
You monitor the replication lag until it catches up perfectly. You stop all application traffic to ensure no new writes occur. You promote the replica in region A to become the primary again. You enable HA on it. You create a new DR replica back in region B. You update your DNS. And finally, you delete the temporary primary you were using in region B.
It is a massive, highly orchestrated operational sequence. It really drives home why these tests are scheduled for 2 a.m. on a Sunday. The deck summarizes the disaster recovery models available for Cloud SQL based on this exact operational reality.
They align perfectly with the hybrid concepts we discussed in the DIY section, just applied to the managed service.
They outline cold DR, which is essentially relying on Cloud SQL's automated backups offloaded to a different region's cloud storage bucket. It provides very slow recovery time, but it's incredibly cheap.
They outline warm DR, which is exactly the architecture we just detailed, maintaining read-only cross-region replicas with asynchronous replication. It offers fast recovery, but you pay for the replica compute infrastructure continuously, and you must accept the manual promotion process and a non-zero RPO.
And finally, they explicitly note hot DR. Hot DR implies zero RTO and strictly zero RPO across geographic regions. Instant automated failover across the country with absolute no data loss. But the deck boldly states a critical limitation.
Hot DR is not available out of the box for Cloud SQL.
Wow, okay.
It is a fundamental limitation of the physics of traditional relational database engines like MySQL and Postgres. They were not designed for multi-region synchronous consensus.
So what do you do if you need it?
If your business absolutely requires hot multi-region DR, the deck suggests two harsh alternatives. You must either rewrite your entire application data access layer to migrate to Cloud Spanner, which is Google's proprietary globally distributed database designed specifically with atomic clocks to solve this problem. Or you have to go back to the DIY approach. You have to build a custom MySQL cluster across two GCE VMs in different regions using advanced third-party replication software, custom load balancers, and highly complex, brittle, automated failover logic.
Which brings us right back to the beginning of the episode. You only take on that operational nightmare if you have a massive engineering budget and an absolute business mandate for zero data loss across a continent.
The architecture always follows the business requirements.
To really solidify this complex web of DIY versus managed, high availability, disaster recovery, and all the architectural trade-offs, let's move to Section 6, Real-World Scenarios. The source material includes several diagnostic questions specifically designed to test this exact knowledge in practical, messy situations.
These are the kinds of scenarios a database engineer faces in architecture review boards constantly. It's about applying the clean theory to concrete, messy business requirements.
Let's whiteboard these together. Scenario 1. An organization is running a highly critical, low-latency reporting application on Microsoft SQL Server. In addition to the core relational database engine, their architecture heavily utilizes extra services. SQL Server Analysis Services, or SAS, for data mining, SQL Server Reporting Services, SSRS for generating paginated reports, and SQL Server Integration Services, SSIS, for ETL pipelines in their on-premises environment. They want to migrate to Google Cloud with minimal disruption to their existing architecture.
The initial instinct for many engineers taking the exam might be to choose the fully managed option. They see the word SQL Server and immediately think, great, migrate them to Cloud SQL for SQL Server to reduce operational toil.
Exactly. I'd assume I just hand the whole mess over to the managed service.
But if you remember the constraints we discussed regarding the shared responsibility model, that is the completely wrong answer.
Why?
Cloud SQL provides the core managed database engine, but it explicitly does not support those ancillary services, SS, SSRS, and SSIS. Those are effectively operating system-level services that run alongside the database daemon. Because Cloud SQL entirely abstracts the OS away from the customer, you physically cannot install them.
So to ensure minimal disruption and keep using those specific data mining and reporting tools, they hit a hard wall with the managed service.
The only valid technical solution for this specific scenario is to migrate to Compute Engine, GCE, and self-manage the SQL Server installation, utilizing the pre-built OS images we talked about in Section 1 to ensure licensing compliance. It's a perfect example of a valid technical constraint forcing an organization into the DIY path.
Okay, scenario 2. You are conducting an internal security and resilience audit, and you realize that one of your critical Cloud SQL MySQL instances does not have high availability enabled. It's currently running dangerously as a single zone instance. You need to follow Google recommended practices to enable HA on this existing instance.
This tests the exact operational mechanics we covered in Section 4. We know you can enable HA on a pre-existing instance without migrating data. The correct method is to execute the API call via the command line. Cloud SQL instances patch instance name dash availability-type regional.
But the slide highlights a critical, almost tricky detail about executing the specific patch command.
The operational reality is that the database instance must be running to execute the patch command.
That seems weird. Why?
Well, an engineer might logically think, I want to be safe. I'll shut the database down during a scheduled maintenance window, apply the HA patch while it's offline, and boot it back up as a fully formed cluster.
Yeah.
But the Google API will explicitly reject the command with an HTTP 400 error if the instance is in a stop state.
Why does it care if it's running?
Because to build a standby instance, the control plane has to cleanly interact with the running primary database to take a consistent storage snapshot to see the secondary zone. You have to issue the patch command while the database is live, and then trust the Cloud SQL automation to orchestrate the required restart and build the standby replica. You have to plan for the brief outage it causes while it restarts.
Wow, okay. It's a nuanced operational detail that proves you've actually executed these changes in the real world, not just read the marketing brochure.
Absolutely.
Let's look at scenario 3. You are architecting a hybrid cloud configuration. You have your primary MySQL data center running on premises, and the physical hardware is getting overloaded with heavy read queries from analysts. You want to create replicas in Google Cloud to scale out those reads and offload some of the management operations, but you are not ready to migrate the primary database yet.
It was a classic transitional hybrid use case. They don't want to risk moving the primary transactional database, but they desperately want to leverage cloud elasticity for the reporting tier.
The options provided in the source include using external server replication manually, using database migration service, writing custom MySQL dump scripts.
The most elegant and fully supported solution here, as outlined in the Read Replica section, is to configure a Cloud SQL for MySQL external replica.
External replica, right.
You securely configure your on-premises database to act as the source publisher, and Cloud SQL spins up a fully managed replica in the cloud that continuously pulls the bin logs from your data center. You get the benefit of managed cloud infrastructure for your reporting tier without touching or risking your primary on-prem system.
Finally, scenario 4, which is the ultimate DR nightmare test. A disaster recovery test concludes. You had your primary instance, DB1, running in region A, and a cross-region replica, DB2, running in region B. During the test, DB1 was forcefully taken offline, and DB2 was manually promoted to primary. The test was a massive success. Now the weekend is ending, and you want to return to the exact pre-test configuration. How do you fail back?
This scenario directly tests your deep understanding of split brain prevention and data integrity. The absolute wrong answer, and the one that causes the most damage, is to simply bring DB1 back online.
Because then you have two primaries.
Yes. If you do that, you instantly have two independent primary databases accepting traffic. It is total chaos.
Another wrong option presented is delete DB2, so DB1 automatically reverts and catches up. Yeah. We know from our discussion that nothing automatically reverts in asynchronous DR.
The correct, painstakingly manual procedure must be followed to guarantee integrity. You must execute the deletion of the original primary, DB1, entirely to mathematically ensure it never receives stray application traffic.
Scary.
You then recreate DB1 as a brand new read replica in region A, configuring it to pull data backward from the new primary, DB2. Once the replication lag reaches 0, you stop application traffic, promote the new DB1 back to primary status, and reestablish your original topology.
It's ruthless. You must burn the ships to ensure you don't accidentally sail backwards into corrupted data. These scenarios really prove that knowing what the technology is, knowing the definition of HA or DR is only a fraction of the battle. Knowing the exact operational sequence, the specific API limitations, and the terrifying constraints of distributed systems is what actually makes you a database engineer.
The theory is always clean on a whiteboard. Cloud operations are messy. The certification tests your ability to navigate that mess safely when everything is on fire.
Which brings us to the end of our deep dive today. We have journeyed from the manual, numbing toil of self-managed compute engine databases, worrying about block storage fragmentation, hypervisor limitations, and complex bash startup scripts. We've navigated the absolute necessity of defining your business rules for failure, having those tough conversations about RPO and RTO.
We moved into the powerful yet highly opinionated boundaries of managed services with Cloud SQL. We unpacked the reality that true high availability requires paying double for a synchronous standby node that you aren't allowed to query, and that routine maintenance still requires taking a breath and a brief pause to prevent the catastrophe of split brain.
And we ventured into the dark art of cross-region disaster recovery, where we learned that to survive the physical loss of an entire data center, you must architecturally accept asynchronous data loss, you must rely on human judgment to manually promote your replicas, and you must ruthlessly delete your old architecture to safely fail back.
It is a deeply complex ecosystem designed to abstract away the physical hardware while still ruthlessly forcing you to confront the inescapable physics of distributed systems and network latency.
I want to leave you with a final thought to ponder based on everything we've unpacked today. We saw that to achieve true out-of-the-box, hot, multi-region disaster recovery, meaning zero downtime and zero data loss across thousands of miles, you have to move past traditional engines like Cloud SQL and adopt next-generation services like Google Cloud Spanner, which uses literal atomic clocks and GPS receivers to enforce global consistency. As cloud providers continue to push further up the stack, releasing these globally distributed, infinitely scaling systems that handle failovers instantly and automatically at the infrastructure layer, will the traditional role of the database engineer eventually disappear?
It's a profound architectural question. If the infrastructure layer becomes truly autonomous, if you no longer have to carefully architect regional failovers or worry about synchronous persistent disk limits or manually calculate replication lag before pressing a promote button,
Exactly. Does the engineer of the future just become a manager of data logic, tuning application queries, defining schemas, and managing access policies, while the cloud itself just becomes an invisible, indestructible, globally persistent hard drive? Are we moving away from the freezing data center towards a future where the database completely manages its own physics? It's something to keep in mind the next time you provision a cluster. Thank you for joining us on this deep dive. Keep questioning how your data is really being stored, and we'll catch you on the next one.